Hello, welcome to lists. This is the first lesson of the data structures course in C where we will actually talk about a specific data structure and how to implement it and some of the caveats. I'm Brian. I'm going to be the instructor for this video and all the other ones in this course. This video assumes that you have already gone through either the previous videos on introduction to data structures and dynamic memory in C, or that you have familiarity with those concepts. So we will not be covering those in any more detail, but we will be making use of them here. Okay, properties of a list. Let's talk about what a list actually is. So a list is something where normally we're always inserting at the back. We're just going to kind of keep a running summary, a running total of the things that we want to add in our list. And adding items at the back is always going to be a constant time operation, order one. This maintains insertion order, so that means that when we go to access the items in our list, we're accessing them from the first item we added to the last item that we added. This usually requires a list iterator. Um, Depending upon how you've written your list, there may be other ways to do it, but the clean way to do it is to write a list iterator that starts at the beginning, goes through each element, and then ends at the end. Finding an individual arbitrary item in a list requires starting at the beginning and going until we find the item or until we reach the end of the list, meaning that the item is not in the list. Okay, so this means that searching a list is an order in operation because it scales directly with the number of items that are in the list. Deleting an item from a list requires first finding it, so that is also expected to be an order in operation. Not all lists support changing an existing value. A lot of times for a list, the operations are just insert and remove. So if you wanted to change a value, you would first remove the one that exists and then add a new one at the end of the list again. For the lists that do support changing a value, you have to first find it. So you have to find it and then modify it. So the combination of finding and modifying would be an order in operation as well because you have to start at the beginning and go until you find it. All right. All of the data structures that we're going to cover can be implemented in different ways, and there's different trade-offs for different strategies of implementing these data structures. For a list, there's two basic kinds of implementations. There are array lists and there are linked lists. The trade-off between these two is that an array list potentially takes up more memory, but they're simpler to implement. They're simpler because they don't have as many dynamic memory operations in terms of creations and deletions, pointer manipulations, and so forth. Uh, Memory linked lists are more memory efficient, but you have to keep track of, what's at a bare minimum what's next in the list, maybe what's next and what's previous in the list. We're going to cover both eventually, but right now in this lesson, we're going to only talk about array lists. They both meet the basic qualifications of the list that we just covered from an outside perspective. But just to get started, let's talk about the first kind of implementation, which is an array list. All right. The reason an array list is called an array list is because the elements of the list are maintained in an array within the list. This is an implementation detail. This is just how we have chosen to implement it for this kind of list. The main container of an array list really only needs to keep track of three pieces of information, which is where the array starts, the number of items that are capable of being held in the array, so the array's overall size, and the number of elements that are currently in the array. Okay, so you notice here I called this that it needs to contain a list of elements. The list is implemented as an array in this case. All right, we can debate terminology, but that's the way we think of it here. The list is the array. Okay, so you see here that in the example I've constructed here, we have a struct array list that holds an integer array, and then the size of the array itself and the number of items that are in our list. Okay, this means that list size is always going to be less than or equal to the array size. It must be in order for this to work. All right, let's talk about array list initialization. So the array list has to always be large enough to hold at least one more item than it currently does. Okay. The only exception to that would be if our memory allocation failed for some reason. And we'll talk about that more when we get to it. But for now, let's just assume that the array list, once it's created in memory, always has enough space to hold one more item. It's recommended that we choose a starting size for the array that's useful for the expected minimum case. Okay, so in this example, you see here I've defined a constant min array size as 4. You need to choose what makes sense for you, given whatever your usage of the array is going, sorry, of the list is going to be. Choose a size that makes sense for you. Um, but do use best practices for defining the size as a constant, as a pound define here. So in this case, we're going to use min array size of 4. All right, so let's talk about how we would create this. So we're going to need 2 memory allocations for this. All right. The first one that we're going to need is to allocate the container, the actual struct array list here. Okay, so you go back here, you know, we have 3 items here, right? And we talked in the overview about using the size of operator and the fact that we can put anything we want in that size of. So we're going to use the size of our array list. And you see here I've defined this type def struct array list, and then I put array list at the end here. So that means we do not have to use the struct keyword. You will always see me define structs this way, so we can just say size of array list here when we're using our malloc operator, and that makes our life easier, that makes our code cleaner, simpler, easier to read and maintain. So we declare an array list, call it array list. We're going to make it the size of an array list structure. Always check our return value for null. If it is null, sorry, nothing we can do. We're just going to return null back to the user. The other thing we have to do, going back here, you look at, we have a pointer to an array here in our array list. And we need that to hold memory, to hold the elements of our list. So we're going to make our array list array an array of integers, because that's what we're holding here in this implementation is integers. And we're going to hold at least the min array size here of integers. Okay, so that happens to be 4. If you decide later that you want to make it something else, we can make it something else. Again, let's check our pointer to make sure that it is not null. So in addition to checking that the array list container is not null, we need to consider if the array list array is null. Check it. If it is, we've already allocated the space for the array list at this point, so we have to free that first and then return null to our user. All right, last 2 pieces of information are the size of the array and the size of the list. The array size is going to be a min array size starting out, because that's what we've allocated it to be. And the list size is going to be 0 because there's nothing in it. So Now we've initialized all three pieces and we can return our array list. Notice here I used malloc for this allocation because I knew that I was going to be initializing all the values myself, and I did not check any of the values to see if they were 0 or anything else, right? I just, as long as I've got a block of memory, I can set all the initialization myself. So I don't need any, special calloc functions here. I can just, set the values myself. Okay, array list insertion. We mentioned at the beginning of this lecture that insertion is an order one operation because we are always inserting to the back of the list. Okay, and what we're doing here is literally just setting the last item in the array and then incrementing the number of items that are in the list. But there's a catch. So remember at the beginning I said that the array needs to always be large enough to hold one more item than it currently holds. So after we've done our insert, we need to check and make sure that's still the case. And if it's not, then things get more complicated. So, let's talk about this. So let's look at our array list insert function here. So we've got our array list and we've got the value that we want to insert into the array. First thing, always check your parameters. Check to make sure that the user didn't pass in a null array list. If they do, just return an error. We're going to return -1 to indicate an error in that case. Also, if the array list's list size is the same as its an array size, that means our previous attempt to resize the array failed, and it's not large enough for us to add any more values to. So we cannot continue. We cannot attempt to resize the array because we've already attempted that once and we failed. So just return -1 back to the caller. If we made it past that, then we know that the array is large enough. So we're going to set the index that corresponds to the current value of list size equal to the value that the user passed in, and then increment our list size. Now, we have to do our checks and make sure that we keep everything sane for the next pass of this if the user calls us again. So if the list size after this insertion is the same as the array size, then we have to extend the array. And what we're going to do here is double the size of the array in this case. So that means if this is the fourth insertion and we just hit array size of 4, then we're going to make a new array size that's twice that. So our new array size is going to be 8. And then we're going to reallocate our array to new array size times size of int because we're making an array of integers. Now you see here I've set the return value of realloc to a void pointer called check. All right, back to our discussion in memory management in C, we can never assign the return value of realloc back to the same pointer that we passed in. All of these functions by default return a void pointer. So we're just going to declare check as a void pointer and make sure that it's not null. If for some reason it is, we are done. There is nothing else we can do. Realloc does not change the contents of the array. So what will happen here is that our array will stay the same, our array size will stay the same, and our list size will stay the same as array size. So that first or second check that we did when we first came into this function that checks to see if list size is the same as array size is going to be met, and the next time a user tries to insert something into this array list, we will detect that case. We will know that we've tried to resize this before and failed. We will not attempt to resize it again, and we'll just return -1 because we assume at this point that the system is out of memory. Assuming that check is not null, that means it's a valid pointer. And so we're going to assign its value to our internal array and then update our array size to the new array size. Okay, so again, if this were the fourth insertion, we just made our new array size 8 instead of 4, and so that's going to be the new array size, and then the list size is going to remain 4 because there are now 4 elements in the array. Assuming that all that went well, we're returning 0 as the status back to the user. Conventionally in C, if you're returning a status integer, 0 indicates good status, and some other value indicates an error. For the course that you're in here, all the examples I use, 0 will will indicate a good status, and I'm going to use a negative value of some kind to indicate an error code back to the caller. Usually -1 is good enough, and so you'll see that used most of the time in these examples. Okay, array list search. So searching a list, any kind of list, requires starting at the beginning, examining each element until we find the desired value. Okay. What we return from a search needs to be some kind of address. Now, that can be one of two things. That could either be the position that the value is found within the list, which is what we're going to return in this case. We're going to return the index of the array that we find it in. Or we could return a pointer to the value in the array or in the list. Okay. And one may be more important or valuable to you than the other depending upon what you're doing with the list. For what we're doing here, having the index of the element within the array is more valuable for the rest of this implementation, and so I've implemented return address of an index here. So that just happens to be what's valuable here, but you may see other implementations that return a pointer. Okay, let's talk about this search algorithm. So, again, as always, check your parameters, make sure that they're valid. If the array list was null, we're done. We will return -1 as the index. Obviously, -1 is not a valid index of an array, so that indicates that we weren't able to perform the search. We weren't able to find the value that was requested. Okay, assuming that the array is valid, we're going to go from the start, which is going to be index 0, to list size, because list size tells us how many valid elements there are in the array, okay, that we've implemented here. So 0 to list size, we're going to check each element if if an element is equal to the value that we're searching for, then we return the index that we found that out. Now, let's talk a little bit about this implementation. A lot of times in C, you'll see for int I equals 0, I is less than something, I plus plus. Okay, that's kind of convention. I recommend anytime you're using an index variable to have at least 2 letters for your index variable. You could write something like for index equals 0, index less than something, index plus plus. That's a little bit long, but if that's more clear to you, you can write it. Or you could use IDX as an abbreviation. I use II because by convention, if we have nested loops, we have I, J, K, etc. So I use II, J, J, K, K. The reason that I recommend having at least 2 letters for a variable name is that it's easier to search for. When you only have a single letter for a variable name and you search for it in a file, you find all instances of that letter that appears in anything. So for example, if I had searched for the letter I in this function, I would find all instances where the word list was written, where the word int was written, right? And any other thing that had an I in it would show up in my search. Whereas if I search for II, that's pretty unique. right? The only places I'm going to find that are going to be in my for loops. So for the rest of this course, in my for loops, anytime I'm writing a for loop that has an index variable, you'll see me use a double letter uh, index variable at least. I may use other variable names depending upon circumstance, but you will always see me write for loops with variables that have at least 2 letters in them, and I recommend you do as well. Okay, if we go all the way through our for loop, all the way from 0 to list size, and we never encountered our value, then the value isn't in our list. Okay, it's not in the list, the array that we searched. So we're going to return -1 back to our caller in that case. Okay, removing an element from a list requires that we first find the element in the list. Okay, that means that we're automatically going to be in order in operation because we have to consider all the elements from the beginning of the list to the point that we find it. In the case of an array list, removing an item is a strict order in operation, meaning that we will always have in operations to do because once we find the element in the array, we have to then move all the other elements from that point onward down one index so that the array contents remain contiguous. Okay. Now, remember I said a second ago that I found it more useful to return an index from the search function than an address. Well, this is the reason why, right? Because if I return an index from that function, then I can use it directly here in this remove function. So rather than rewriting all the logic to find the item in the array, I can just call my array list search function with the array list. If the value that's returned is less than 0, I know it's not in the list. Now, also, because I know that array list search checks for whether or not array list is valid, I know that it cannot return a value greater than or equal to 0 if our pointer isn't valid, if our pointer is null. So I don't have to check for array list being a null pointer again in this function. The array list search has already done that for me. So this is an example of code reuse. It also makes this code simpler and shorter and easier to maintain. So I'm going to call my search, look for the value. If I don't find it, I'm done. I just return -1 back to the caller to indicate I couldn't do it. If I make it past that, then the value that I found, the index that I found, is greater than or equal to 0. Okay, so from that point onward, I need to move everything down. Okay, so each element from that point onward, I'm going to set equal to its neighbor 1 after that. So this is literally a index for index copy all the way down. And once I've done that entire range, then I'm going to decrement list size. Note that I'm only going to list size -1 because by nature of removing an element, I have decreased the number of elements in the list. Uh, but we're not going to do that until after we successfully do all the copies. Okay, so decrement the list size, and then we're going to return good status back to our caller. All right. We talked about iterators a little bit at the introduction to data structures. So an iterator is something that allows for traversing a data structure from its beginning to its end. In the case of an array list iterator, it holds a pointer to the array list that is iterating over and the index of the next value to return. Okay, so it's a very simple structure, right? So we have our array list iterator, AL iter, that holds our pointer to our array list, and an integer that indicates the next index that we want to return the next time we access the value of this iterator. So how do we create and initialize one of these things? Okay, well, if the array list is non-empty, then initialization will return a pointer to a new array list iterator. So non-empty means that the array list can't be a null pointer and the list size can't be 0. Okay. If the array list is empty, if either one of those things is true, if it's a null pointer or the list size is 0, we're going to return null and we're done. And we'll get to the specifics of why this matters in a minute. Okay, assuming that the array list is not empty, then we need to allocate enough memory for the size of our ALITER structure. Okay, so we're going to use our handy size of operator, allocate that number of bytes. Always check your pointer for null. If it is null, return null. There's nothing else we can do. Memory allocation has failed, so there's not enough memory to do anything. Assuming that that succeeds, we're going to set the array list equal to the array list that was passed in, and we're going to set our next index to 0, so the very first index of the array list. And then we are not going to free the array list iterator in this case because we're going to turn that back to the caller of this function. Okay, iterating an iterator. Okay, so anytime we increment an iterator, we're going to prepare it to get the next value that is part of the list that we're iterating over. Okay. If the next index in our array list iterator is less than the size of the list, not of the array, but of the list, the number of elements that are valid within that array, then the function is going to return the array list iterator that was passed into the function. But if the next index is going to be equal to the size of the list, meaning that we have now exhausted all the elements that were valid within the array, then we're going to destroy the array list iterator that was passed in. We're going to free the memory and then return null. And again, we'll see why this becomes important here in a few minutes. So again, first things first, when we go through this function, check your parameter, make sure that it's not null. If it is null, just return null and you're done. We're going to increment the next pointer. Okay, so we're going to say we're going to go to the next element in the array that we're maintaining within the array list. If once we do that, we are at the value of the list size within the array list, we are done. That means that this iterator has already evaluated all the elements of our list, of our internal array, and there's nothing left to evaluate. If we had tried to access the array index at that value, at that index, it would be either garbage or potentially a segmentation fault. It would potentially crash the program. Hopefully, if we'd done this right, it wouldn't, but it could. So when we reach that state, we know that we're already at the end, so we're going to free the array list iterator that was passed in, set our pointer to null, and return null. Okay. Assuming that's not the case, assuming that we're still within the bounds of the list size, just return the pointer that was passed in. And we're good again. Okay, last thing an iterator needs to do is be able to access the value that it is currently set to. So getting that value is just a matter of getting the value at the next index that we're storing in our iterator. Okay. we should not need to check for null for an array list iterator or for any iterator. I'll show you why here in just a second, but remember that our previous function does does return a null pointer in the event um, that we're at the end of our list, but it is the responsibility of the user of an iterator to check for a null iterator. That is the usual flow of using and incrementing an iterator to its end. So we're not going to check for a null here. We're just going to look up the value that we're storing and return it. And if you think about it, that makes sense, because if we did have to check for a null, what would we return in that case? Usually when we return a value from something, from an iterator, we're returning the value at that location. We're returning a valid value. If we're trying to test for an invalid situation, but we're always returning a valid value, what do you return to indicate an invalid value? That doesn't make any sense, right? So we're going to say that the responsibility for checking a null iterator is the responsibility of the caller of this function. The caller should not call this function if the iterator is null. Now let's look at an example to see what I mean here, okay? So usually with an iterator, we do this with a for loop, okay? So I've got a function here that's going to print out all the contents of an array list with one element per line. I'm just going to use printf to do that. Okay, so again, as always, first check to make sure our array list isn't null. Okay, if it is, return -1. We're done. Print out a message. This is what we're doing. We're printing out the array list contents, so array list contents, colon. All right, let's talk about how we do our initialization and checks for end here. So what we're going to do is declare an array list iterator by passing in our array list to ALItter create. Okay. And the test condition for our for loop is that our ALItter is not null. Okay, so remember a second ago I said that it's the responsibility of the caller to make sure that the iterator passed in to get the value isn't null. This is why. Because making sure that the array list iterator isn't null is our stop condition for our for loop. Okay, so we should be guaranteed, because of the structure of the for loop, that anytime we call ALItter value, that the ALItter isn't null, because if it was null, we wouldn't be able to enter the for loop in the first place. So we're using this as a check and a guard against the rest of the for loop here. And the incrementer for our for loop is going to be setting ALItter equal to ALItter next of the ALItter. And remember what this function does here. It updates the state of the iterator to point to whatever the next value is going to be. And if it detects that that value would be beyond the end of the list, it destroys the iterator and returns null. Okay, so we don't need to do any freeing or clean up of memory here, because that's what the ALItter create and ALItter next functions automatically do for us to keep everything sane and well bounded within the context of a for loop. So ALItter equal ALItter create of the array list, go until that pointer becomes null, increment one at a time by calling ALItter next of the ALItter. And each time that isn't null, each time we get a valid value passing through this for loop, we're going to print out the integer at that value with a new line after it. Okay, so let's see an example of how we would put all this together. So we're going to include our array list.h, which has all the definitions of the array list and the array list iterator structures in it, as well as all the prototypes for these functions that we just talked about here. We're going to create our new array list with array list create. we're going to insert items into our array list. AL list insert, and here I've just done 7 items, 1 through 7, 1, 2, 3, 4, 5, 6, 7. Print our array list. Then we're going to remove the value 4 from our array list and print it out again. So the second time we do a print, we're going to get 1, 2, 3, 5, 6, 7. Okay, because of the way that we've done this. Now, note, we don't have to do any checking for array list after we do the array list create, because all of our functions manage that for us. If we wanted to exit main early, we could. Totally valid to do that. But because we know that we've written all of our functions correctly, we don't have to do that for the functions here. We would just not get any output if something failed. Okay. Exercises. Right now, we have a bug with the insert and remove logic, because if a value is inserted twice, it's going to be added to what was the end of the list in 2 separate occasions. If we then call remove, we only remove the first one we find. We don't continue to search the list beyond that. So really it would be ideal if we don't allow duplicates. So really what we should do here is change array list insert to first search the list and see if the value is already there. And if it is, just return an error. Don't attempt to insert again. Don't allow a duplicate to be inserted into the list. So go through that, see if you can do that. You should have all the tools, I think, at this point to do that. I'm going to post a link to the code that's in this slide deck, as well as the slide deck in the comments of this video, so you can look at the library and figure out how to do the modifications for that. Okay, exercise 2. We have another issue here that we never implemented a way to destroy an array list. There's no way to free the memory. If you go back and look at our main function, we don't do any cleanup. This is very, very bad practice. So make an array list destroy function that takes a pointer to an array list and frees all of the memory that it's using and returns null. Okay, so you can look at the array list create function, and if you go review the dynamic memory section of this course, you'll see that I recommend always freeing in reverse order of creation. Okay, this is another example of why that's a good idea. So your array list destroy function should free things in the inverse order that things were created during array list create, and then return null back to the caller. And then modify the main function in that example we just had so that it properly frees the memory and sets the pointer to null before returning. Now, because you're returning null from your destroy function, instead of having to write 2 separate statements, you can write just one, because you can set the return value of your destroy function to your array list parameter that you pass in. And then when that function completes, your pointer is going to be null at the end of it because it returns a null back to the caller. Okay, exercise 3. Write an array list get function that takes a pointer to an array list and a desired index within the list. So if your list holds 5 items and you pass in, say, the index 2, then it will get the 3rd item of the list. Okay, 0, 1, 2, that's the 3rd item. And make it return a pointer to the element if there are enough items in the list. Okay. Remember that the syntax for getting a pointer to an element in the list is ampersand array and then bracket index bracket. Okay. If the user specifies an index that is beyond the end of the list, then make the function return null. All right. That way it's clear to the user either I got a valid index or I didn't. Okay, it's one of the two. So see if you can do that. See if you can make a function that returns the index, a pointer to the index on success, returns null if that specified index is beyond the end. Okay, last thing. This is extra credit. So the array list that we defined in this lesson holds int values. Now, your real list that you're going to use in real life could hold ints, but they could hold doubles or floats, or they could hold strings. So copy the implementation that we have here to array list string and change it to hold C-string values. For this, your internal array is going to be an array of char star pointers. And each time a user does an insert, you'll need to allocate memory for each string. Remember that you're going to need to use the string length and string copy functions to make a copy of the values that are inserted to the list. And don't forget to account for the terminating null byte at the end of each string when you go to allocate memory for each of the strings that you're going to wind up copying into. Okay. When you're doing your search function, in order to do a search or remove, you'll need to use the string compare function to compare those values. And when you're modifying your print function for printing out the contents of the list, you'll use the %s formatter with printf, so you can print out the strings that are part of your list. Now, just a heads up, we are going to be using strings in the next lesson when we talk about linked lists. So this is potentially beneficial for you, but it is extra credit. You know, if this is too much too soon, that's okay. We will take it a little bit more step by step in the next lesson. So that's it. Next time we'll talk about linked lists. So good luck with the exercises and the extra credit. Have fun.